Hello, now we move on to the next, which is a Wien bridge oscillator. And at the end of this topic, students should be able to describe the operation of Wien bridge oscillator, draw the waveform associated with the oscillator, analyze the Wien bridge oscillator circuit, and derive the transfer function of the feedback network, and then determine the frequency of oscillation of Wien bridge oscillator, and lastly, how to design a Wien bridge oscillator. This is the circuit of a Wien bridge oscillator, comprised of an non-inverting amplifier. There is no phase shift between the input and the output. So if you look over here, the input and the output over here will be in phase. So for this particular circuit, it uses RC series. In series, you have C1, R1 in series and another pair of RC which is parallel. So Wien bridge oscillator is RC oscillator, and both of these series and parallel RC is combined, and this will determine the frequency of oscillation F0 for this circuit. And Wien bridge oscillator consists of two feedback. The first part is the negative feedback, comprised of the amplifier. It is non-inverting amplifier, and the other part is the positive feedback. So if you look over here, VO is taken and being fed to the positive terminal of this circuit. So this is the feedback network and this is the amplifier. Now we move to the feedback network. The feedback network just now consists of two series and parallel RC pairs, and I define the current over here, and the current over here can be considered zero since there is no current entering the op-amp. So with that, we left with just a series RC over here, and I call these two as Z1. The impedance, the total will be R1 plus the impedance of this capacitor. So it is R1 minus JXC1. Minus JXC1 is 1 over J omega C1. And for this R2 C2 which is parallel, Z2 will be R2 multiplied with the impedance of the capacitor divided by R2 minus JXC2. Substitute the impedance with 1 over omega C. So R2 multiplied with 1 over J omega C2 divided by R2 plus 1 over J omega C2. So with Z1 and Z2, we can simplify the circuit to be this way. So it's just a Z1 comprised of this series RC and Z2 which is the parallel RC. The feedback voltage VF over here is the voltage across Z2. You have input to the circuit which is your output. So we can use a voltage divider where VF, the voltage across Z2, will be simply VO multiplied with Z2 divided by the total impedance. Right here, VF equals to VO multiplied with Z2 divided by Z1 plus Z2. So with this, we can find the beta for the Wien bridge oscillator, which is defined as feedback voltage divided by the output voltage. It is simply Z2 divided by Z1 plus Z2. Okay, so we have defined Z1 just now. It is in series R1 minus JXC1, and for Z2 it is R2 parallel with JXC2. So substitute this value into this. Okay, you'll get that this is for the Z2, this is Z1 plus Z2. Simplified, and you can get that everything is multiplied with R2 minus JXC2. The numerator will become just minus JR2XC2 from here. You multiply with R2 minus JXC2. So this R1 minus JXC1 will be multiplied with R2 minus JXC2. So this will simply minus JR2XC2. This one is cancelled out. So you open the parenthesis for this. Okay, R1 multiplied with R2, and then R1 multiplied with minus JXC2, minus JXC1 multiplied with R2, minus JXC1 multiplied with minus JXC2. Minus minus is plus, J is J squared, XC1, XC2, and plus will minus JR2XC2 becomes minus JR2X2. And if you remember that J squared is minus 1 and 1 over J is minus J. So substitute this, J2 is minus 1. Over here you minus J, and you will come to this. Your VF will equals to R2XC2 divided by R1XC2 plus R2XC1 plus R2XC2 plus J in bracket R1 R2 minus XC1 XC2. Okay, so this is the feedback which is beta, okay, defined as VF over VO. And from this equation, the imaginary part, which is this part, must be equate to 0 in order to find the frequency of oscillation. Remember, the oscillator must satisfy the Barkhausen criteria. Okay, the imaginary part equals to 0. So you equate R1, R2 minus XC1, XC2. From here, equate it to 0. And from there, simplify. Okay, R1, R2 equals to XC1, XC2. Substitute XC, which is the reactance, is 1 over omega C1. XC2 will be 1 over omega C2. And this is equals to 1 over omega squared C1, C2. So we want to find what is this omega. This omega squared is 1 over R1, R2, C1, C2. Okay. And from there, the frequency of oscillation, we call it omega naught, is equals to 1 over square root of R1, R2, C1, C2. Okay. You have R1, C1, R2, C2. This is in radian per second. Or in hertz, it will be F naught equals to 1 over 2 pi square root of R1, R2, C1, C2. Okay, so this is the frequency of oscillation. But if the value of R1 and R2 are equal and C1 and C2 is equal, so this is just R, this is C, the frequency of oscillation can be simplified as omega naught equals to 1 over RC. In radian per second or in hertz, it will be F naught equals to 1 over 2 pi RC. Okay, so we can determine the frequency of oscillation using the value of RC at the positive feedback. Okay, and for the amplifier over here, it is a non-inverting amplifier. Remember, this is the input VF coming to the positive terminal of this op-amp. So it is a non-inverting amplifier with a gain of 1 plus RF over RA. At the frequency of oscillation, just now we have defined omega naught is 1 over RC. So reactance of your capacitor XC1 is equals to XC2 because we just simply say it is a C, and reactance is 1 over omega C. Okay, just substitute omega naught is 1 over RC. So C cancel out. So the value of the reactance is equals to R. So meaning that at the frequency of oscillation, the reactance of this capacitor are equals to the value of the resistor used in the circuit. So with that, from the equation of your beta just now, you substitute XC1 equals to XC2 and it is equals to R1 equals to R2 and simply it is R into this equation. Okay, if you substitute everything, R2 is R, XC2 is also R, R1, R, and everything. And similarly for this part, R1, R2 is just R, XC1 is R, this is also R. Simplify this equation, R minus R will be 0. R plus R will give you 3R, okay, 3R squared, okay, so R squared, this part 0, so you left with 1 over 3. So at the frequency of oscillation, the beta is equals 1 over 3, okay, and using the Barkhausen criteria, beta A must equals to 1. So now we know that beta is 1 over 3 and A just now is 1 plus RF over RE. So beta multiplied with A equate it to 1, and with that we can know that the ratio of RF over RA must equals to 2. This is another way of finding the frequency of oscillation. Okay, we just analyze the positive feedback, and similarly we can simplify the circuit. The 2 in series as Z1, the 2 in parallel is Z2. Okay, and your beta is VF over VO. Okay, just substitute Z2 because this is 2 parallel. It will be R2 multiplied with the impedance of the capacitor divided by R2 plus over 1 over j omega C2 divided by all this in series. So R1 plus 1 over j omega C plus these 2 in parallel. Okay, so this is another way of finding the frequency of oscillation. Just now I have shown the easiest way to find the frequency of oscillation. With this, you can still find the frequency of oscillation, but it will involve some mathematical manipulation, and if you do it right, you should be able to get the equation equals to 1 over 1 plus R1 over R2 plus C2 over C1 plus J in bracket omega C2 R1 minus 1 over omega C1 R2. So from here to here will involve several steps. Okay, and with that, again, equate the imaginary part to 0 and find the omega. This omega is actually omega naught, and you will get that the omega squared equals to 1 over C1 R2 C2 R1, and your omega naught is equal to 1 over square root of R1 R2 C1 C2, which is equivalent with the one that we have derived before. And if the value of the resistor is just R and the capacitor is just C, your omega naught will equals to 1 over RC. That is in radian per second, and F naught will be 1 over 2 pi RC. It is the same equation, okay? And at the frequency of oscillation just now, omega naught is 1 over RC. Substitute into the equation of beta, and you will get the same value. Your beta will equals to 1 over 3, okay? This is just another way of finding the frequency of oscillation and finding the value of beta, okay? Now, we know that the feedback network or the Wien bridge oscillator will reduce the input signal by 1 over 3. Beta is 1 over 3. And the frequency of oscillation is actually the frequency of resonance, because the reactance of the capacitor is equals to R. And if you plot the frequency response curve, this is what you get. Okay, it is increasing at the frequency of resonance, which is the frequency of oscillation. Your V out will be 1/3 of your V in, because the feedback network will be an attenuator, and then it will be decreased with increasing frequency, and the frequency of oscillation is also the frequency of resonance is 1 over 2 pi RC, and the frequency response is actually a band pass with a narrow bandwidth with a high Q. Okay, so this is the frequency response. And if you look again for the circuit just now, this is the feedback. The beta is 1 over 3. This circuit will fulfill the Barkhausen criteria. The loop gain A, 3, beta is 1 over 3. A multiplied with beta equals to 1. And just now, the gain is positive, and we get that beta is also a positive value. So the total around the loop, which is the phase shift, is 0. Okay, so this is just another way of drawing this circuit. These two in series, these two in parallel can be redrawn like this. R1, C1 is this part. Okay, RC parallel, it is thing. Okay, this is coming to the positive terminal of your op-amp, which is your VF right here, going in, and CR going to VO. So this CR going to VR. This is just another way of drawing the Wien bridge oscillator. In this one, it is clearly seen it is a bridge. And lastly, for Wien bridge oscillator, in order to start the oscillation, actually, you should make that your RA is a variable resistor, because just now we know that RF over RA must equals to 2. But in order to start the oscillation, we make the RA slightly less than the initial value, so that RF over RA will greater than 2, so that your open loop gain will greater than 1. So it will start oscillate, and once the A multiplied with beta equals to 1, it will sustain the oscillation. Okay, the loop gain is 1, so you get a sinusoidal waveform. Okay, and usually we put a back-to-back Zener diode. This is to limit the output. Okay, so this is another way of starting the oscillation in the circuit. Instead of using R2 as a variable resistor just now, but we put an additional R3 over here, but it is parallel with a 2 Zener diode. Okay, so the gain will be 1 plus, the RF will be R1 plus R3 divided by R2. So R1 plus R2 will be slightly greater than 2. So it will start oscillate. Once it is oscillate, this Zener diode will clip the circuit, and finally you get the circuit to oscillate at the frequency of oscillation. Okay, and a sinusoidal waveform will be produced. So this is the end of the Wien bridge oscillator. Thank you.